Hello there, welcome everybody. Today we're going to talk about geoprocessing, very common term that we use in the GIS field when it comes to running various types of analysis regarding, one or more multiple pieces of data. Usually it's a plural type of endeavor where you have, 3, 4, 10 different things, whatever it is, and you're asking yourself, can a GIS do some kind of function? For example, something as simple as, I have 2 different layers and I want to merge them into one thing, into one layer. The location information, the features, and the attributes. Just in general, that right there is called a geoprocess, okay? And there's several of these types of processes. So the goal of today is to go over the theory behind some of the most common ones, and so that you understand the terminology and things that will come up, like I say, on a regular basis and a daily occurrence for anybody working with GIS moving forward. So first, let's talk about what's called the overlay analysis, okay? An overlay, what does the term overlay actually mean? Well, an overlay is the process of, or the technique of taking, two different things, at least 2 different things, and kind of, stacking them on top of each other, right? Now, I don't mean physically they have to be in the same location necessarily, but you have more than one. Well, actually, in this case, we are talking about proximity-wise, kind of creating a stack of. We know that layers stack on the table of contents, but I'm talking about the actual locations, the physical locations themselves, stacking layers on top of each other, right? And that's called an overlay. When we talk about an overlay, we're talking about investigating the spatial association of features by vertically stacking. Exactly what I said, feature layers. And we want to investigate geographic patterns and determine location information based on specific criteria. So we talked about at the beginning of the semester, the doctor who in England who was trying to understand the cholera outbreak. And what he did was he took these wells, water wells that people would drink from. And, so that was one part of data, location wise. And then he took another piece of data that was the locations of where people were getting sick. And he went, wait a minute, let's see if there's a correlation between these 2 things. Let me stack them on top of each other and wonder if that's going to overlay them on top of each other and wonder if that's going to describe any kind of pattern. And it did, right? It did show spatially that the locations of at least it theorized that, okay, this well over here has a lot more cases to it location wise, and so if we shut that valve off, maybe that will, let's see what happens to the cases after that. And it worked. It essentially determined that people that were going to that well that was contaminated were the ones that were getting sick, okay? And so that was a version of an overlay analysis, in a GIS that you could imagine, right? At least theorized. So early times, we're talking about anything related to like even hard copy maps, one and here, and stacking on top of each other and seeing what kind of spatial patterns exist, right? The same map, same locations, but now stacking on top of each other. It's kind of the foundation of what GIS is in general, right? Overlaying these different things. So yeah, here's a little story about that just on this first page to kind of reemphasize what we're talking about here. And we talk a lot about vector and raster in this module. At least the terms come up. We're going to focus on the vector portion here because that's what we've covered so far in the course. There is some raster discussion later on that's coming up, but for now we're focusing on the vector stuff. So even though it might say raster models in some of these things, I'm really only going to lecture on the vector types of analysis, vector types of geoprocessing. Okay, so that leads me to vector overlays. Okay, so vector overlays. So predominantly overlaying various polygons on top of each other, right? And it could be, you know, dozens of polygons that are kind of, you know, randomly overlaid on top of each other, stacked on top of each other, right? And so, yeah, we'll get to other options here in a moment where we can take, because remember, vectors are points, lines, and polygons, right? Three things. And you can mix and match those as part of an overlay. But first and foremost, we'll talk about the polygon types of functions. So there is something called an intersection. Let's see. So these are polygon to polygon types of vector overlays. Superimpose over one polygon to create a new output polygon layer. Yeah, this is really important. The resultant polygons may contain some or all of the attributes from the polygons which they were created. So oftentimes you have two separate things and you're overlaying them, and the result after you do the analysis is a brand new third thing that gives you the you know, gives you the results of what you were trying to come up with in the first place. So like, for example, an intersection type of analysis here, right? This is a type of geoprocess. You'll find this. This is a term, common type of vector overlay geoprocess. So an intersection, for example, say you have vector A and B, right? Polygon A and B, and they're stacked on top of each other. In a certain portion is where they actually overlay, right? They don't completely overlay, but there is a portion here, you know, where there is some connection made there. And so you run an intersection process, and the result is, let's call it C, would be this little kind of crescent shape, which is, okay, we sliced out that little piece where they connected to him, where they were connected to one another. We sliced that little piece out, and now C is all that's left over, and that is our intersection. It's a new polygon. It's a new layer, right? It's going to be a new file altogether. So other types of overlay, polygon to polygon, is a union. Okay, union. So again, A and B example, and they're connected somehow. Well, let's turn them into one polygon, right? Now, with the union, let's see. Yeah, important note about the union is that it still maintains this little portion here where the intersection exists. There is another function out there, I believe the merge, which is going to essentially erase this as being a unique part of the feature, the new feature. So your boundary would be continuous from the outer portion here, boom, boom, and there wouldn't be any additional part of the feature, you know, out there on its own. Just saying. I'm only giving examples here. So this is the union, like I was mentioning. Clip, okay, a clipping function, clipping overlay function means that you are going to cut a piece of something away by using the boundary of something else. So for example, A and B. Well, if I want to clip A, right? So I want to clip A based on B, right? So this would be my input feature. This would be my clipping feature. Then the result is going to be something like this, right? Something like this, where now the intersection portion actually is removed from A. And, you know, depending on how you want to set up the criteria, it could be the other way around. It could be the other way around, where you go, okay, actually, I want B to be my input and A to be my clip. Well, in that case, then you would see something like B having, you know, this portion of the intersection be removed, right? So you'd have kind of like a circle with a straight portion to its edge there. And so there are dozens of these types of functions, these types of vector overlay process. But yeah, we're going over some of the most common ones just so we have some understanding. And a lot of times the terminologies are like added to each other. So like a clip and merge or something. We see this kind of stuff very frequently. So let's also discuss overlaying polygons to points, and that's possible as well. Now that's actually called, and you have some experience with this now, right? This is called a spatial join. Okay, spatial join. So what we're going to do is, okay, we've got all these polygons. Imagine these are some parcels of something, and we've also got some features as single points. So we've got a point layer and a polygon layer. And if we do a point to polygon geoprocess based on the vector overlay in the GIS, we end up with this spatial join where it could go either direction, depending on, again, which one is the input, which one is the influencer kind of thing. So it could be that the result is a point shape file with all of the attributes associated, with all of the attributes appended. That means we added the attributes from the polygon to the new point file, or it could be the other way around, right? So that's what this would be about. Okay, you could definitely, yeah, you can't merge these two things. Almost misspoke there. You can't merge these two things into one single layer because you can't have, just based on the properties, you can't have a polygon. You can't have polygon features and point features all in one layer, right? Layers have to be one of three things: points, lines, or polygons. But you can take the attributes and, you know, mix those around, right? Based on a spatial join. And the same thing can be done with lines to polygons or lines to points, right? Or lines to points. So there's three ways to go about it there. Just another type of spatial join: line to polygon, superimposed over the polygons. Lines are superimposed over the polygons. And so again, the goal there is to append the attributes from one to the other. Okay. Let's keep going here and talk about a different type of geoprocess called neighborhood operations. And so there are a number of types within this as well. Neighborhood operations are, let's see, more related to a proximity analysis. Okay, so consider the characteristics of neighboring areas around the specific location. What we're saying here is that you don't necessarily have to have two independent things become, you know, one new thing. In this case, say you have one layer and you want to analyze it and determine something about that layer, and, you know, give you a new one as your result. So like, for example, like I say, well, hold on, back up for 1 second. Like it's saying here, the functions either modify an existing feature or create new feature layers, which are influenced. And it's, again, these are based on some type of distance. Some type of distance is part of your criteria that you're developing here. Okay. Let's see. Yeah, I'm skipping a couple of these because neighborhood operations are very common with raster functions as well, which we will cover when we talk about the raster section. So I'm just going to go over a few of them that are vector related. Buffering, extremely common type of process. They are the most used neighborhood operation. So this is not a great graphic, I know, from the text, but basically what happens here with a buffer, you have a layer, and it could be a specific feature within that layer, like maybe it's, you know, a bunch of roads, and you have one road in particular that you want to analyze. And you say, okay, for this road here, give me a new layer and show me all where if I went out from the center of the road out, kind of like a radius, if I went out in the direction of say 200 feet away from that road, create a new polygon around my road based on that criteria. Create a buffer, right? It's pretty straightforward, just like the name sounds. When you have a buffer, you create a zone around something, right? Some kind of subject. So that's what buffers do. And buffers are really common, relating to different types of assets or, line features in particular, but certainly polygons and even points, right? You could do points. So say you have a point and you wanted to know, give me a circular, a point is not, there's no real shape. It's just a dot, right? So now give me a circular shape, polygon, give me a circular shape around that point where my radius is, again, 100 feet, let's say, or 100 meters or 1,000 feet or whatever it is, right? And so what happens is you have your point in the center, and then all of a sudden, boom, you've got this big circle around that point. Well, that whole thing is, again, a type of buffer. It's a buffer is what you just created. So you went from a point to now a polygon. And so that's useful in the sense of, something simple like, the cholera thing. So here's the well. I know this is the contaminated well, and create a buffer of 100 feet around that, and we'll have to tell everybody within that neighborhood, within that 100 feet, that you're, could be infected by this contaminated water, right? That's just an example. It could be essentially anything, right? That's why buffer is so commonly used. Let's see. Most buffers use constant widths to generate zones. Yeah, so create a buffer around layer X with a width of 200 feet, something like that, right? Roads, right-of-ways, again, asset type management, a lot of civil type of work. Buffers are, you're going to run a buffer at some point in time with that type of data sets. Let's talk about Thiessen polygons, proximal polygons. So I haven't really used something like this myself very often, but I could see, based on the information here, where this could be handy. So with Thiessen, you're creating new boundaries around points. Very similar to what we just talked about, but now, let's see, delineate territories within any sides closer to the internal point. So it's like you're creating I guess they are buffers in a sense, but you're creating, but in this sense, they're not at consistent, widths around the features, or consistent radius, or even consistent shapes. So you're saying, okay, based on the random spacing of these points, create polygons around them, and we'll designate each of those polygons as specific zones. So it's like saying, okay, give me, it's looking at all of this spatial, the distance between these various points. And then it's saying, okay, what would be the, if we had polygons all interconnected with one another, right? Notice how each one of these edges connects to one another. If they were all connecting to one another, without crossing over, without crossing each other, if they were connected without, but didn't cross, what would be how would the polygons, flush out? What would they look like? And so that's what this does, right? I'm sure this could have come in handy at some point for me. I just haven't really thought about using this, but it's definitely something out there. Okay, so continuing on here. Oh no, my little Buffering around. Oh, that's interesting. Okay. I just noticed that I have a typo. This figure 5.5 should have been up here. Interesting. I'll have to fix that. Anyways, okay, let's keep going and talk about connectivity analysis. And with connectivity analysis, so what we're doing here is we're going to be analyzing a network of data. So when I say network, I'm talking about some sorts of data sets that are related to one another, and all have some kind of common cause or use, but they're different types of data sets, right? So maybe it's maybe it's we want to, and this is a little bit deeper, right? Relying on more of the AI that's going to exist, the AI functionality within a GIS process itself. But let's see, accumulate over areas traveled. So say you have a network of roads and towns, whatever it is, right? You're trying to, maybe it's like in the example we have in a moment ago that I'm going to show you in a moment. We have various fire station locations. So the network analysis is saying, here's the data, tell me the best route or the best, most cost-effective way to figure this out, or the fastest from one place to the other. So I think the best way to describe this is to actually just break down how these different connectivity analysis types are out there, starting one at a time. So network analysis, I kind of saying this interchangeably, but network analysis, let's see, the flow of networks, a connected set of lines and point nodes, sometimes called centers and hubs. So linear networks, like I was saying, roads are linear, right? They're lines. So it's like you have a connection of lines and points, and what type of questions are we trying to solve, or things are we trying to solve based on these lines and points. So let's see, point nodes usually represent a pickup of destination sites. Okay, so just putting that out there, right? Each linear feature affects the resource flow, okay? So now we're also taking into account the attribute information, in addition to, so it's like running a location and attribute analysis all at one time, if that makes sense, right? So before we were talking about really everything based on location only, not really taking it. Well, I guess this one takes into account attributes, but most of these are location-based types of geoprocesses. Whereas now, when you get into the connectivity stuff, these take into both things, right? So let's see. Okay, stuck valve might allow too much resource. Network analysis tools can help analyze the cost of something. Let me see. Let me read from what my notes say. Network analysis analyzes the flow of something. Okay, usually linear features and points. So this is good for cost and resource analysis. Let's put it that way: cost and resource analysis, taking into account both location and attributes, all in one kind of go here. All right. So three major types of network analysis include, let's see, first and foremost, let's talk about route selection. Attempts to identify the least cost route. This could be as simple as the least cost is saying the shortest distance, really. And so a route selection, you have to have, again, let's think about what needs to be part of this. So you have to have some type of linear features or feature, and you have to have at least two nodes, right? Could be the start and end of where that line is. The route selection is the simplest form. Something as basic as you go into your car and you're going to go drive somewhere that you don't know the exact best route to go in. And so what do you do? You enter your, well, it already has your location based on, let's say if you're using your phone, that's the first node. Okay, that's the first node. Then you say, okay, here's my destination. That's your second node. What happens is the route selection looks at the network of all of the roads, okay, all of the roads around you between those two nodes, and it says, based on all of that information, just distance-wise, this is the fastest, or this is the shortest distance, right? This is the shortest distance. Now, to take that a step further, if you have navigation that's also accounting for, say, traffic, or if you wanted to throw in a criteria of where are the next gas stations, things like this, right? This is all part of connectivity analysis slash, under the guise of network analysis, right? So all of that functionality that's occurring when you open up a GPS, app is taking into account route selection and running. So how does it know traffic or dynamic things like that, traffic or points of interest like gas stations or food or something? Well, those are attributes, right? Those are attribute things. And so it's going to be analyzing all of that at once. Okay. Okay, so let's see, resource allocation, define the nodes and analyze the network. Define the nodes and analyze the network features given a criteria. So this is, in this case, again, we start with the nodes and we tell it, instead of, just going from one place to another, in this case, we're saying, okay, define like specific territories, define specific, the best use of resources based on the network that we have to work with and the nodes. So for example, like in this one, we have a 4-minute response time of 6 fire stations, each one of these little triangles being fire stations, okay? And it's analyzing all of the network of all these different roads here. And it's telling us, okay, based on this location information, the polygon that is drawn around each station represents the area that can be covered in 4 minutes. So it actually went through and it created polygons based on the points and the lines, and then created polygons saying, okay, well, these are, this is how far out we can go. So it's not a simple little radius that was created here. But yeah, these would be the, kind of reach of how far out we could go. And this is the city of Bellingham, I believe, in Washington State. Anyways, that's resource allocation. Okay, so taking that information from your network, and in this example, basing it from a node and having the lines, determining how far out the lines would go, and then kind of redrawing what that parcel would look like. Okay. Now, let's see, network modeling. Again, these are all interconnected or interrelated to each other. This is similar, except in this case, we're modeling. When we say modeling, it's saying, okay, based on the information and the data that we have, what is this going to look like in the future, right? If we make some modifications, how would our sample, how's it going to respond, right, to the real world? So whenever we create a model of something, it's like the intention is to, ask questions and predict answers of the subject based on the model that, that's why it's a model. You could tinker with it without affecting the actual thing, right? And so modeling is within that vein. We're saying that, let's see, resources like water and traffic are placed in a network and the movement is modeled, right? So yeah, identify problems with the network So it could be, trying to model better routes if we were going to construct new roads or something like that, or model, like in this case, water, water flow. Maybe there needs to be more drains installed in a specific area that has a lot of flooding or something like that, right? So you can model out like, okay, so what would it be like if we installed drains here, here, here? And, again, based on the network, boom, here we've just created what the outlook should be like, right? So yeah, these are, I would say, more advanced. Actually, really all of these, maybe not the route selection so much, but at least the resource allocation and network modeling are more advanced geoprocessing. You're first going to come around with doing some of the simple things, and even myself, I still do these things on a very frequent basis, that are kind of built in and baked into the software, the geoprocessing tools that we've talked about. Each one of these is its own. I know we're talking about them in terms of being in terms of what they do and the theory behind them, but like a buffering is a tool. So you could say run the geoprocess tool, the buffer tool, or the buffering tool, and that's going to fall within geoprocessing. Okay. Cool. Okay. I think that's going to do it. So thanks for watching, and hope you enjoy. Have a good rest of your day. Bye for now.